Okay, let's look at a few easy examples about determining where a function is increasing and where the function is decreasing. So according to that theorem in the previous video, we'll go ahead and call that the first derivative test. We just need to see where the derivative is positive and where the derivative is negative. So here's just some examples. Where is the function increasing and where is the function decreasing? So here's a function, f of x equals x squared minus 2x plus 1. Take the first derivative and we get 2x minus 2. And so this thing factors. I would recommend factoring anytime you get a chance. So 2 times x minus 1 is the result. And we can see visually once we factor it that x equals 1 is a critical value, a critical point, right? That's where the derivative is equal to 0. So we want to check on either side of where the derivative is equal to 0 and see where it's positive and where it's negative, right? So here's how you can do that. I'm going to mark the critical value down. So, right, mark all the critical values down. And then we just want to sort of check convenient numbers. So off to the side here, I will list the factors of f prime. So here we've got 2 and x minus 1. So I'll list 2 and x minus 1. And now the number 2 is always positive. So I'll put big plus signs here. Now check convenient numbers to the left of 1. So like 0 is a convenient number to the left of 1. So I plug 0 into this thing and I get a negative number, right? And now I want to check a number to the right of 1. So like 2 would be a convenient number to the right of 1. So when I plug in 2, I get a positive 1. So now I get a negative and a positive, and so now you want to just multiply all of these things together. So here I'm going to get a negative, and here I'm going to get a positive. So the derivative is negative everywhere on the interval from negative infinity to 1. So we can see that the thing is decreasing, right? Decreasing on the interval from negative infinity to 1. Right, and the thing is increasing on the interval from 1 to infinity. Right, so this would be a good final answer for where is the function increasing and where is the function decreasing. By the way, here's what this thing looks like. Right, x squared minus 2x minus 1, right, it's decreasing until you get to 1. And by the way, what happens when I plug a 1 in here? I'm going to get a 0. So there's a 1. It's decreasing until I get to 1 and then increasing after 1. Right? So this thing looks like what we expect it to look like. That is a parabola that opens upward, and it's got a single x-intercept at x equals 1. If you like, the y-intercept is at y equals 1, right? So basic graphing stuff, you can check and see that this thing actually looks like this. But the main point is to see that it's decreasing to the left of 1 and increasing to the right of 1. Also notice that when we go from decreasing to increasing, we get a local minimum at the critical point x equals 1. So this is also a good way to check for relative extreme points. So local mins and local maxes we can check using the first derivative test. All right, here's another example. This one will have a few more critical values. So here's the function 3x to the 5th minus 5x cubed. And so we want to know where the thing is increasing and decreasing. So take the first derivative, factor it. I would set it equal to 0 so you can find the critical values, and then you know exactly where to check. So the derivative is going to be 15x to the 4th minus 15x squared. And now you can factor a 15x squared out. You'll be left with x squared minus 1, and that's going to factor as x plus 1 times x minus 1. So just by inspection, you can see that the critical values will have 1 at 0, we'll have 1 at negative 1, and we'll have 1 at positive 1. This is where the derivative is equal to 0, by the way. And so I'm going to take these critical values and plot them in order on a line. So negative 1, 0, and 1. Off to the side, I will write the factors of the first derivative. So 15x squared, x plus 1, x minus 1. You can write whatever factors on the side look convenient to you. For example, I could have broken this up as 15 and then x squared and then x plus 1 and then x minus 1, but right, whatever is comfortable for you. So what do we know about the sign of these things? Well, 15x squared, that's positive no matter what. So in any one of these intervals, I'm going to get a positive number. Right, what about x plus 1? A convenient number to the left of 2, or sorry, a convenient number to the left of negative 1 is negative 2. When I plug in negative 2 here, I'm going to get a negative. A convenient number between negative 1 and 0 would be negative 1/2. So here I'm going to get a positive. If I check positive 1/2, I get a positive. If I check positive 2, I'm going to get a positive. And so that takes care of that line. And now what about x minus 1? If I plug in negative 2 here, I get a negative. If I check negative 1/2, I get a negative. If I check positive 1/2, I'm going to get a negative. And then when I check positive 2, I'm going to get a positive. So now since we multiply all of these things together, I want to multiply all of these things together. So plus times minus, that's going to be a plus. Positive, positive, negative is a minus. Positive, positive, negative is a minus. And then positive, 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 that's going to be a plus. So I can see exactly where the function is increasing and exactly where the function is decreasing. So it's increasing, right? The thing is increasing from negative infinity to negative 1, and then from 1 to infinity. Right, so this would be a good final answer for where is the thing increasing. And now where is the thing decreasing? I'm going to go ahead and say that it's decreasing from negative 1 to 0 and then from 0 to 1, right? We don't say that it's decreasing at 0. The derivative is equal to 0 at 0, and so there's really nothing happening there. So I suppose I'm not going to be too picky about that. So it's decreasing from negative 1 to 0 and then from 0 to 1. So this would be a good final answer for where is the thing increasing and where is it decreasing. Okay, so let's do a quick sketch of this function 3x to the 5th minus 5x cubed based on the information that we found in just a second ago. So we know the thing is increasing from negative infinity to negative 1. And then it switches to decreasing. And then after 0, it stays decreasing. And then it switches to increasing to the right of 1. So it looks like here we should have a local maximum at x equals negative 1 and a local minimum at x equals positive 1. And so here are the critical values plugged into the function f just to see what the y values are there. So I know at negative 1, right, at negative 1 I'm going to get a 2. At 0 I get y equals 0. And then at x equals 1 I get y equals negative 2. So how do we connect these dots? Well, it goes from increasing to the left of negative 1. And then after negative 1, it starts to decrease, right? And then it decreases till we get to 0, and then it continues to decrease, right? And then after positive 1, now it starts to increase. So here's a good sort of rough sketch of what this function looks like. All right, let us just close with this. This theorem here. And this is the first derivative test for local extreme points, right? So suppose x equals c is a critical value, so a critical value of f. And if f prime changes sign from positive to negative, so if f goes from positive to negative, then that means that f of c is a local maximum. So if that change happens at x equals c, then f of c is a local maximum. if f prime changes from negative to positive at x equals c, then f of c is a local minimum. So we saw a picture of that, so there's probably not much need to write down a proof, but we saw a picture of that in the last two examples. So this is something to keep in mind for this curve sketching business.